Welcome back, guys. Hey, now it's starting to we went over this a lot in Patho. We're going to go over it really deep now, which is basic chemistry. And it's so very important to understand basic chemistry in the fact that a lot of our drugs work off of these chemical principles, and a lot of what we do for our patients work off of these chemical principles. If you do not understand these principles, you're asking for trouble, okay? You're not going to understand what happens, when, and how. And again, it can be very detrimental because it affects the way that you would treat a patient. Let's start with some basics here. Again, matter, anything that takes up space and has mass. And then mass, of course, is a physical property that determines the object's weight based upon the Earth's gravitational pull. If I was to stand on the moon, I would probably only weigh about 70, 80 pounds. Again, that's due to the gravitational. My mass hasn't changed, but the gravitational force has. Oops, sorry guys. Let's try that again. So again, basic chemistry, these are the elements. And elements are the fundamental substance that compose matter. Again, we have 105 of them, maybe 106. I think they just came out with a new one. But again, those were artificially made. But your basic ones are the ones that appear on a periodic table of elements. So most of that's in our body, again, the percentage of the body is mostly oxygen, some carbon in there, hydrogens, of course, nitrogen, and that's probably mostly in our lungs. And then again, the different other trace elements that you might have. Again, there's a lot more of the trace elements down here that's totaling 0.1%. So again, notice that a lot of these, if you look at these things, by the way, we talk about potassium a lot when we're talking about drugs, chlorine, sodium, magnesium. We're adding those things in order to make somebody get better. The reason, by the way, calcium is such a big one is because calcium is used for muscle contraction. And, of course, a lot of what our muscle mass is, again, is that it's going to require a lot of calcium. Also, we got our bone structures in there as well, which, again, use calcium. So again, most living organisms need about 20 elements to survive. Again, and your atoms is the tiniest particles. And again, actually the tiny particles are proton, neutrons, and electrons in there. So that is the smallest components of an element. Okay. Now, again, atoms are composed of subatomic particles that we just talked about right there. And then the atom's mass determines the number of protons and neutrons that are in the nucleus. So again, back to where we were talking about it in pathophysiology. Your protons and neutrons form the nucleus of the atom, the middle of the atom, okay? And it depends, and that's what actually gives it its atomic number. Now these guys up here, again, electrons, they orbit the nucleus of the atom. And this is where your interactions happen. And again, remember our first valence shell, these guys here, the first one's only got the 2 electrons. And then as they go out, they have additional electrons. So again, your second valence shell would have no more than 8. And what it's trying to do again is to fill up those valence shells on the outside so that it becomes stable. Now hydrogen, this guy again, he's only got 1 proton and his atomic weight is 1. Where magnesium has 12 protons, where its atomic number is 12. And then again, your atomic weight of that is also has to do with the number of neutrons that's in the nucleus. These are not negative or positive particles, but again, so like oxygen has 8 protons, 8 neutrons, so its atomic weight would be 16. Now your isotopes, these guys, they could or could not be radioactive, but basically it's the number of the protons are the same, but different number of neutrons, okay? And usually when it's got too many neutrons, it's being held together by additional energy. It, again, tries to get back to a normal state. It decays that, and that's what radioactivity is the releasing of those energetic particles, and that's the radiation that it is releasing. Again, occurs due to an unstable atomic nuclei. Again, they want to get back to a homeostatic or what they're supposed to be normal. So again, the radioactive decay would be an example of the process of emitting radiation. Now, we actually do use these in a good way in certain cases. We use it when we're doing imaging, of course, to determine whether or not somebody has an abnormality. They will inject it with a radioactive isotope, a very low level of radioactive isotope, in order to see better on the X-ray or the examination. And again, by the way, those emissions can destroy molecules, cells, and living tissue. So again, that's why we don't use anything dangerous when we're doing the X-ray studies. And then again, we use that again as a diagnostic tool. As a matter of fact, we use it a lot. Our three types of radiation, by the way, I would probably know these three. You're going to see these somewhere in the near future. Again, alpha, beta, and gamma. Alpha, usually extremely large. Usually a simple piece of paper will stop those. Beta, usually a layer of clothing will stop beta radiation. And of course, gamma, it is the most penetrating and is similar to X-ray radiation. High amount of energy it can do. But again, as far as doing damage, by the way, alpha will do the most if it gets inside. The problem is it has a problem getting inside. Same way with beta. It has a major problem. But the gamma radiation, again, very penetrating. It can very easily do that. Now, molecules are any chemical structures that consist of atoms held together by bonds or covalent bonds, okay? So again, two atoms of the same element, they can bond and they can produce a molecule of the element. So again, hydrogens can do it, oxygens can do it. Again, O2 is a stable gas. And again, it shares 2 electrons from each of them. Same thing with nitrogen. So they're able to have that. Now, your chemical bonds is, again, it's where they share or gain or lose electrons. And by their gaining and losing electrons, they basically form a covenant, if you will. They get where they bond together. Again, inert atoms are chemically inactive, and then ions, again, are atoms that either gain or lose an electron. The example that I would use there for ionic bonds would be your salt. Sodium, usually positively charged. Chlorine, usually negatively charged. Chlorine wants to get that ion. In sodium, it has an extra electrode in the valence shell. So what it usually likes to do is give up that electron. Now, when I say of all those things, I bring this back to cations and anions. Anions are a negatively charged particle. So in the example, I use table salt. Sodium, again, is the cation, and the anion would be chlorine. Okay, so that would be the example that we use. So again, your covalent bonds, again, they share electrons. They do not gain or lose them. They simply share them. And of course, the good example of that one would be water. Now, the thing with water, by the way, and we're going to go through it. So again, a covalent bond here, again, the hydrogen atom, that would be forming a covalent bond. Okay, and it can be single bonds, it can be double bonds, it can be triple bonds, as a matter of fact. And that's, by the way, why carbon works really great with bonding to things. And as a matter of fact, it has its own little branch of chemistry called organic chemistry. And I will tell you that, again, that can be literally those are 2 semester-long courses that you would have to take if you were going to move on to the medical career. Now, your covalent bonds, by the way, polar molecules. So you can every now and then, what happens is one end becomes slightly negative, the other positive. And the biggest one that I can think of that has the polar molecule is water. And the problem is that you would think that structurally that they would keep the hydrogens on both sides. But what happens is actually they kind of rotate around. But this gives them a slightly positive and a slightly negative charge, which allows it to attract. And that's why, again, water, again, it's a wonderful molecule in the fact that it does so many things, probably the simple basis of life for us. So it allows us to gain a small, slight positive or negative charge. And this becomes really important when we start talking about cell membranes, because we'll talk about the permeability of those cell membranes and the water, whether it's water soluble or not. So again, these are very important concepts to understand. Now, compounds are molecules that are made up of different bonded atoms. So water is a combination of hydrogen and water and oxygen. Again, your molecular formula for that would be H2O, or HOH is another way that you can write it. Again, your structural formula is used to signify how they're joined and arranged, okay? And so usually when they do a 3D model of these, and again, if you did a 3D model of it, you would probably see a hydrogen with the oxygen in the middle. Now, reactions. again, when they give up electrons or receive electrons, they react to each other to form a more complex structure. These usually require a certain amount of energy in which to do that. And so for growth and repair, we have to do that. And again, a synthesis reaction, if you add A and B, it becomes AB, but it usually also requires, what they don't show you in here is it usually requires a little bit of energy in which to do this, to get these two together. So decomposition reactions. Our food would be a good example of decomposition reactions. Hydrochloric acid breaks this down. It goes into our blood. It goes into the gastrointestinal tract, where it's broken down even more by digestive enzymes. So it breaks down, especially sugars, proteins, fat molecules, and then allows us to absorb it. Now, again, these usually require energy and or some other physical action or chemical reaction to happen. And we can also have exchange reactions within the body. Again, if we got A and B together, and then the second molecule is C and D, but we need A and D together with C and B, usually with a little bit of energy and breakdown reactions in both ways, we can actually form these things as well. We can reverse it. By the way, these happen all the time. Succinylcholine is a great example of it stops the it allows us to stop that reaction of resetting a nerve. So we have these reversible reactions that happen in our body all of the time. But we, again, it's not the again they are reversible reactions, and there's a lot of biological reactions that are freely reversible. If you're doing the muscles, you're moving the muscles, it requires again all the tissue to be moved along with the electrical systems to be activated, deactivated, reset. So all of these things are reversible reactions within our body. Enzymes. These guys, they lower the activation energy requirements. Digestive enzymes are a good example of that. It's less energy in order to break them when you add these enzymes together. There's some that actually activate the chemical process, and some that just kind of regulate it or accelerate it, or in certain cases slow it down just a little bit, so that it can be permanently changed or consumed. Now we're going to hold off here because, again, this next part, again, we're going to start getting into acid-base balance and the pH scale, and of course that's kind of a big one. So I'll see you guys on the next video.